All right, today we're going deep, right down to the microscopic level, to break down the science behind one of the most famous and infamous viruses out there, the human immunodeficiency virus, or HIV.
And it's a really good question, right? How can something so incredibly small, just a tiny little particle made of RNA, have such a massive, world-changing impact? Well, that's what we're here to do. Let's break it down.
So, first things first, what is HIV really? To understand how it works, we have to get to know its fundamental nature. At its heart, it's part of a very unique and, honestly, a very clever family of viruses.
So what's the big deal? I mean, there are tons of viruses out there. What sets this one apart? Well, to get that, you have to look at its genetic instruction manual. See, unlike a lot of viruses that use DNA, HIV plays a totally different game.
Okay, so this is where it gets really interesting. HIV is what we call a retrovirus, and that name is perfect because retro literally means backward. You see, in most of biology, the flow of information goes from DNA to RNA. But HIV, it flips the script. It carries its genetic code as RNA and then uses a special tool, an enzyme, to rewrite that RNA code into our cell's DNA. It's working in reverse, and that single trick is the secret to its success.
All right, next up, how this thing actually attacks. Now that we know what it is, let's look at how it puts that retrovirus strategy into action. And its main target is, well, it's pretty ironic, the very cells designed to protect us from invaders.
So the journey starts with transmission. Once it's in the body, the virus acts like a professional thief. It's looking for one specific target, our T cells. It uses two receptors on the cell surface, CD4 and CCR5, almost like a key for a very specific lock. Once it unlocks the cell and gets inside, it performs that reverse magic we just talked about, weaving its own generic code right into our DNA. And that is its genius, really. It becomes a part of us.
And here's the really sneaky part. Once it's integrated, the virus can just go dormant. It can go quiet. We call this latency. This viral DNA, now called a provirus, can just hang out inside our cells, completely hidden from our immune system, sometimes for years. It's the ultimate Trojan horse, just waiting for the right moment.
And all of this leads to the single most critical outcome of an HIV infection, the one thing that really defines its damage, a drop in the number of these CD4 T cells. This is the absolute hallmark of the infection, because these cells are like the generals of our immune system army.
So why do their numbers drop so dramatically? Well, it's basically a three-pronged attack. First, as new viruses are built, they have to burst out of the cell, and that damages it. Second, our own immune system is smart enough to see that these cells are now virus factories, so it attacks and destroys them. And finally, the virus can actually send a signal to the infected cell, telling it to self-destruct. It's just a devastatingly effective strategy.
So if this virus is so good at hiding inside our own cells, how on earth do we even find it? That brings us to our third section, the incredible science of diagnostics.
These days, the standard screening test is an absolute powerhouse called a fourth-generation immunoassay. And what makes it so smart is that it's not just looking for one clue. It looks for the antibodies our body makes to fight the virus, and it looks for a little piece of the virus itself, a protein called P24. That combo makes it really, really good at catching the infection early.
Okay, so let's walk through a common scenario. Imagine someone takes one of these screening tests and the result comes back positive.
But then, a second, different kind of test, what we call a confirmatory test, comes back negative. Whoa, so now you have a conflict. The first test says yes, the second says no.
This is a really important moment. So what do? How do you figure out the truth when the tests don't agree? This is where we bring in the big guns. The tiebreaker is a test that goes straight to the source. It's called a nucleic acid test, or NAT. Instead of looking for antibodies or bits of protein, it looks for the virus's actual genetic material, its RNA. It's the most direct way to prove whether the virus is there or not.
But, it's never that simple, is it? No test is perfect 100% of the time. And when it comes to HIV, timing is absolutely everything.
And this slide highlights two of the biggest challenges. On the left, you've got this thing called the seroconversion window. That's just the tricky period right after someone is infected, but before their body has had time to make enough antibodies to be detected. A test taken in that window could come back negative, even if the person has the virus. And on the right, you have the challenge with infants. A baby gets a ton of antibodies from its mother, so a simple antibody test can't tell if the antibodies belong to the baby or just leftovers from the mom.
And that brings us to our final and maybe most important section, living with HIV. Because thanks to decades of absolutely incredible research, an HIV diagnosis today is nothing like it was in the past. So let's look at the science that made that transformation possible.
The absolute game changer was something called antiretroviral therapy. These drugs are brilliant. A lot of them, like one of the first ones, zidovudine, are called reverse transcriptase inhibitors. I know, it's a mouthful, but it's actually pretty simple when you break it down. Remember that special enzyme the virus uses to work backward, reverse transcriptase? Well, these drugs simply inhibit it. They jam the gears on the virus's replication machine, stopping it from making copies of itself.
So, to make sure the treatment is working, doctors track two key numbers. First is the CD4 T cell count. This tells them how healthy the immune system is. Is it getting stronger? And second is the viral load. This literally measures how much virus is floating around in the blood. The whole goal of therapy is to get that CD4 count up and the viral load way, way down, ideally so low that it's undetectable. So when you step back and think about it, we've gone from this tiny piece of RNA to a global crisis. And then, through sheer scientific will, we've turned what was once a near-certain death sentence into a manageable, chronic condition. It's just incredible. Which really leaves us with the ultimate question as we look to the future. What comes next?